Now let's cover the continuous perceptron. So in this case, we're going to replace the threshold logic unit that we had here with the sigmoid activation function, meaning that we have our x1, x2, so our input pattern, x1, x2, xn, which is fed to this perceptron. And then we have an augmented pattern, y, because we're setting the threshold here, wn plus 1 here, so that we have at the input here, xn plus 1 equal y, 1. So instead of having a threshold, so w1 x1 plus w x2, so the summation, the activation is fed in this case to a sigmoid activation function, and that's for two reasons. The first one is we're going to gain final control over the training procedure, as we're going to see later in our in our training rules. And then we're going to facilitate the differential characteristics to enable computation of the error gradient. Meaning if we use the threshold logic unit, which is discontinuous, which is non-differentiable, we will not be able to use it with, in this case. So we use the sigmoid because it's differentiable. And the same procedure, so we have at the output of the activation function, the sigmoid, we're going to have the actual output, which is compared to the desired output to give us an error, which is equal to 1/2 of d minus o. So the desired output minus the actual output. And then this error here is going to help us adjust the weights of the perceptron. And we're adding the 1/2 here. It doesn't affect the location of the error of the minimum in our error function. It's just for mathematical convenience that we do that. So in this case, the updated rule would be the new weight would be equal to the old weight minus a learning constant, eta, times the error gradient of the current error function. So this is the gradient, and the error function is given by this formula. So the new weights are obtained by moving in the direction of the negative gradient, just like before, along the multidimensional error surface. So in this case, in our weight space, in this case, for illustration, we're just showing W1 and W2, but we're going to have in the weight space, we're going to have an error function. And if this is our initial weight, so we're going to, with training, we're going to converge to the global minimum, hopefully. So this is the contour. This is the error contour here of this function. So if we start here, W equals 0 is the initial weight. So we move along the negative gradient along this multidimensional error surface. So the first training, we move here. The second training, we move here, and so on until we get the error equal to 0. We go to the minimum here in this case. And then that would give us the final W1F, W2F, which would be the final weights that we will use to test our learned perceptron. So again, this the error final is less than the fourth error here. It's less than E3, it's less than E1, and so on. So we define the error as the square difference between the desired output and the actual output, as we've seen. So the error is 1/2 of d minus o square, or we know that the o is the activation, W transpose times the y, the pattern, the input pattern, and then we feed it to the activation function. And this is the net activation, okay? So it's 1/2 of d minus f net square. Now, we need to take the gradient of that because this is used for our learning rule. We need it here. So if we replace our error by 1/2 of d minus f net square, and we take the gradient here. By definition, this is the partial derivative of the error function with respect to the first weight, the partial derivative of the error function with respect to the second weight, and so on, up to n+1, because the dimension of our weight, we've seen that it's from W1 to Wn+1, where Wn+1 is the threshold. This is equal to, if we apply the rules of differentiation, so this is equal, so the gradient of this, or the derivative of this, the 2 and 2, they cancel. We're going to have a minus sign here, and then d minus O, and then we apply the chain rule, so it will be f prime net times the error, the gradient, or the partial derivative of the net activation with respect to W1, and the partial derivative of the net activation with respect to W2, up to n+1. So because net equal to W transpose Y, so we have delta net, the derivative of net with respect to Wi, equal to Yi. So we replace this here, so this would be Y1, this would be Y2, and so on. So this would be, this vector here would be equal to the input pattern Y. So the gradient would be equal to minus the desired output minus the actual output times the derivative of the activation function times the input pattern here, Y. So this is the training rule of continuous perceptron, which is equivalent to the delta training rule, okay? And so back to here. So the new weight would be equal to the old weight minus eta times this gradient. And this is the learning rule. So this is the way we adjust our weight according to this formula. But we're going to see here, instead of computing the derivative, we're going to see that the derivative of the sigmoid is actually given in terms of the input and so on. So we're going to show that it's very easy to compute this gradient and therefore to adjust our weights. So in the case of the bipolar continuous activation function, so where bipolar meaning that we have +1 and -1, so we're going to have f net equal to 2 times 1 plus exponential minus lambda net, the net activation, because that's the input to the activation function here. If we compute the derivative, if you follow mathematical, you know, just differentiate 2 divided by 1 plus exponential minus x, exponential minus lambda x. And so you find that the derivative of this is equal to lambda times 1 minus O square. So this is very convenient because you know the actual output. So the f prime, so the updated rule or the learning rule would become the new weight equals to the old weight plus this formula here. And the delta, this is the delta W. And then you can see here that all these terms, so desired output, actual output, and the input pattern, okay? So it's very easy to compute this update, you know, to update our weights with this, with the bipolar continuous activation function. And it's the same thing for the unipolar continuous activation function. So in this case, the formula for f net is different. So f net is equal to 1 divided by 1 plus exponential minus lambda times net. So if we take the derivative of f prime of net, so just like if you take in the derivative, so for example, if you have your function is 1 divided by 1 plus exponential minus x, and you want to take the derivative of x, so it's very easy. You compute it just using the you know, the normal derivative rules and so on. So you'll find here in this case that f net, f prime net is equal to lambda times the output times 1 minus the output. So our learning rule becomes the old weight plus eta times lambda d minus O, and then this, the delta W, this delta W here, is a function of the desired output, the actual output, the input pattern, and then here it's the learning rate. We'll cover more about the learning rate and see how to make it adaptive in the case of the multi-layer perceptron later. This lambda here is this, if we've seen how this lambda affects the shape of the sigmoid function. Now, if we use fnet equal to this, to this formula, so we look at the same example as we've seen in the case of the discrete perceptron, but with an activation function that is continuous, meaning that we use this activation function here, the bipolar. So it has this formula, okay? Fnet is equal to this formula. And we feed the same patterns as before, as in our previous example. So the first pattern is 1, 1. Second pattern is minus 0.51. Third pattern is 3, 1. And then the fourth pattern is 2, minus 1. And we're going to see, because we're going to have an explicit expression of our error functions, that the error function for E1 looks like this. E2 looks like this. E3 looks like that. And E4 looks like that, okay? So let's look at the general formula for the error function. So it's given by 1 minus the desired output minus the f of net, which is the actual output, which is given when we're using the bipolar activation function, is given by this formula here, okay? So for E1, which means that this input pattern Y1, so this is equal to 1, 1. So in the net 1 would be W1 plus W2. So that's easy to compute. We know that pattern 1 belongs to class 1, so D1 is 1. And then we have everything defined here. We set lambda equal 1. And when we reduce and simplify our expression, this expression here, we find that E1 of W equal to this function here. If you draw in the W1, W2 space, it looks like this function here, okay? And you can see that this error here is just a function of the weight parameters, W1 and W2. Same thing, you can do the same thing by looking at the second input pattern, Y2, which is minus 0.5 and 1, and you do the same procedure. You find an expression for E2 that you can draw here. The same thing for E3, same thing for E4. So these error surfaces are as shown on the previous slide. So if we combine them, our total error is equal to E1 plus E2 plus E3 plus E4. We combine them to find the total error, which looks like this. And this is the global minimum for this error function. So we would like to start from, if we start our weight W1, W2 at somewhere here, after training, we would like to end up in this, at this location here, in this minimum. And you can see here that the trajectory from arbitrary weights, initial weights. So if we start here, so you can see that after a number of training, we converge to here. If we start here, same thing, we converge here. If we start here, we converge here, and so on. And we're going to, and there is actually a proof to show that we converge to the error, to the, in this case, to the global minima after a number of finite iterations. So a finite number of iterations. Okay, thank you.